If you think about nuclear energy, probably one of the first things that comes to your mind is a nuclear bomb. Uh, this is a mechanism that releases massive amounts of energy on an extremely large scale, starting with a relatively very small mass. In this video, we're going to look at two types of nuclear processes, one being nuclear fission, the other being nuclear fusion. We're going to look at their similarities and we're going to look at their differences. The first nuclear process we're going to look at is fission. This is the most common process, the one that we're most familiar with. When you think about an atomic bomb, when you think about a nuclear power plant, this is the nuclear process that those things are based off of. In nuclear fission, what happens is we take uranium-235. Uranium-235 is a radioactive substance, but it's relatively stable. Now, what happens in fusion is that we shoot a neutron. So this neutron, we shoot that neutron at that uranium-235 nucleus. When it attaches to that nucleus gets very unstable. And it gets so unstable that in less than a second, in a fraction of a second, it splits apart. And that's what fission is. It's a larger atom. And typically it's a uranium-235. It's a larger atom splitting into smaller atoms. And here we have krypton 92 and barium 141, the smaller atoms that it actually fizzes into. Now, if you look at this equation, you'll also see that there's some energy released. And this is just for one fission reaction. So 200 mega electron volts. Now, where that energy comes from, we're going to look at the calculation and how we can actually determine that in the next video. But Albert Einstein, when he came up with this equation, E equals mc squared, he came up with a relationship between energy and mass. And just looking at this equation, we already know that c, the speed of light, is a very big number, and it's squared. So based off of this equation, very small changes in mass are going to result in a very large amount of energy being released. And so that's kind of the foundation for these nuclear processes and why so much energy is actually produced. We're going to talk about something called mass defect in future video. But that mass defect is why so much energy is produced. Right now, though, we want to look at this fission reaction. Now, one thing you'll notice in this fission reaction as well is when that uranium-236 nucleus splits into two smaller nuclei, it also produces 3 neutrons. So those 3 neutrons go shooting out from that uranium-236. Right? So it goes shooting out in that process. Now, those 3 neutrons are able to repeat this process, where they can collide with the uranium-236, bind to it, become uranium-236, and then a chain reaction will occur. So typically when you see a nuclear bomb, when you look at very large amounts of energy being produced, it's because of this chain reaction. So this process is repeated over and over and over again, and it increases exponentially because each fission reaction is producing 3 neutrons. So this is the process that we use in our nuclear power plants. It's a relatively easy process to control because by controlling the amount of uranium that's available for collisions to occur, we can control the amount of energy that's going to be released. So that's fission. The other process is one that we're not very good at yet, but it does occur in our sun, and this is nuclear fusion. What you'll notice here is we have 2 hydrogen nuclei. We have deuterium, which is 2 nucleons, and then we have tritium, which is 3 nucleons. And they fuse together to form this helium nucleus. So this is the process of fusion. So in that process, we form a helium nucleus and 1 neutron. So that's a fusion reaction. This is a process that's very hard to perform on Earth because to take two hydrogen atoms and bring them very close together, we're fighting that electric force between those protons. They want to repel each other. So it takes very large amounts of energy right now and very high pressures for that process to occur. When we try to do this on Earth, we end up putting in more energy than we actually get out just to get those hydrogen nuclei closer together. Now, there is a fusion reactor in our solar system, and that fusion reactor is the sun. At the center of the sun, there's such high temperatures and high pressures that fusion is able to occur. So fusion is actually the driving force of the sun's energy. And actually, because of fusion, 73% of the sun is hydrogen and 27% is helium. And that helium has come from this fusion process. You'll notice that this process also produces energy, and again, that we can use Einstein's equation, E equals mc squared, to see the relationship. Very small changes in mass are going to produce relatively large amounts of energy. Now, comparing these two processes is difficult if we look at just the total amount of energy produced, because both of these processes have different amounts of nucleons that are actually participating. But if we want to compare them, we can compare what's called the energy per nucleon. So in this process, we release 200 mega electron volts. However, in fission, 236 nucleons are present. So in reality, this is 0.847 mega electron volts per nucleon. If we look at fusion, this is 17.6 mega electron volts. However, there are only 5 nucleons participating. So we do this calculation, and that's an energy change of 3.52 mega electron volts per nucleon. So this is one of the reasons why there's a lot of research being put into producing nuclear fusion reactors. Because we produce so much more energy per nucleon compared to fission. We haven't figured out how to perform it yet in a way that is efficient. But one of the other upsides of fusion is that we produce helium. Helium is relatively stable and safe, whereas right now in fission reactions, we produce a lot of larger radioactive atoms that take a very long time to break down. So there's kind of a safety factor with fission, whereas fusion, if we could perform it, the products are relatively safe and we produce more energy per nucleon. So finally, just to compare and contrast fission and fusion, in fission, larger atoms are split into smaller atoms. Whereas in fusion, it's the opposite. Smaller atoms are joined together. Now, both of those processes release large amounts of energy. So we can still, so they are still similar in that aspect. However, in fusion, there's more energy per nucleon released. Both of these are nuclear processes. Now, one of the downsides of fission is that we produce larger radioactive products that take a long time to break down. However, fission is easier to perform and control. Fusion requires very high temperatures and very high pressures in order for it to occur. That's why the only place in our solar system that we're aware of it occurring right now is in the sun, where there's very high temperatures, very high pressures, and so fusion is the engine that drives the sun. On Earth, we can perform fission, and that's what we do in nuclear power plants, and nuclear bombs are another example of that fission chain reaction.